All right. Welcome again. Today we're gonna do a recap of chapter 7. Let's get started here. So chapter 7, actually, this is very important chapter that is gonna be heavily expanded on for next semester in the CNG 4351. This is where we talk about traffic control, analysis of signalized intersection. We started first with a brief introduction on um, basically roadway intersection. If we did not have the concept of intersection, then our life as transportation engineers would be much easier. But the issue is having an intersection. Once we do have intersection, that means potentially we have three different possible movements from each direction. So that's actually 3 times 4, that is 12 possible movements, plus, or if we consider pedestrians from 4 directions, so that's actually 4 pedestrian movements. So total you have 16 possible movement or conflicts, if you will, at the intersection level. And that is a lot of activities right there that can contribute to the reason why we have a major source of crashes and vehicle delays happens mainly at intersections. And that's why we have to have certain control over those intersections, whether having um, the simple stop sign or always stop sign or real sign, all the way up to a signalization of that intersection. And we mentioned that to get an agreement or to get the okay to have a traffic signal at certain intersection, we have to satisfy at least one of those warrants that we're going to talk about next semester. We also went through the advantages and disadvantages. I'm not going to go through them again, because again I've discussed them in the recorded lecture. But if the traffic signal is designed well, we will reap the advantages of having a traffic signal. Um, but if they are not designed right, or if there was no need to have a traffic signal there, maybe a stop sign or an all-way stop sign or real sign would have worked, but we insisted to put a traffic signal. It may actually introduce certain types of delays, as well as certain types of accidents, sadly to say. Also, the cost is not that cheap to just to install a basic signal installation on one of the four legs. It's about $100,000. And if you are talking about a four-legged intersection, we are talking about roughly $500,000 worth of an investment to signalize one single intersection. So it's not an easy decision if you are a traffic engineer for the city trying to put a traffic signal at an unsignalized intersection. And that's why MUTCD have 8 different warrants or 8 different conditions. You have to satisfy at least one of them in order to justify the need of having a traffic signal at this location. We also did define what do I mean by an intersection versus an approach versus a lane group, and we've looked at this picture. So be prepared again. If you see this in an exam or an interview, you should be able to tell where is the intersection, how many lane groups do you have per approach, and how many approaches. So that's also important. And then we also define now what are the components of a signal cycle. A cycle is really, again, a signal cycle is one complete rotation through all of the indications provided. And that cycle has a length in seconds. It can be as low as 30 seconds or as high as I have seen 210 seconds or even 270 seconds. Within each cycle, there is multiple intervals, and we've talked about these again in the recorded lecture, but basically these are the change interval, which is the yellow time, where again, you're changing now from moving to stopping. You have the clearance interval, which is the all red time. So many of us may not realize this by now, but when you are approaching an intersection and it just turned red on you, you also for a couple seconds you would notice that even in the opposite direction there's no movements, and that's why, because we have this all red, which can last somewhere between 2 to 4 seconds, really to get it's give another chance really to someone who is getting closer and closer to the intersection and they want to clear. How can we let them clear the intersection safely? Is it legally? Maybe not, but this is now engineering versus legality. Here again, we're adding those 2 to 4 seconds just in a hope that this may help. But again, a careless driver is a careless driver, and this may not work and may not help all the time. And then we have a green interval. This is again self-explanatory here, where people are allowed to cross the intersection, and we have a red interval. And also we have phases. Phases, again, a signal phase consists of actually a green interval plus the change and the clearance interval. So for every cycle, we may have 2 or 3 or 4 phases depending on the case. So if I'm drawing here an intersection, sometimes the first phase will be to let the northeast, I mean north-south movements first, and then that's considered the first phase, and then maybe the second phase would be now the east and west movements, and maybe that's it. So some, again, a minimum of 2 phases. Or if we have a significant amount of left turners, we actually may end up adding now more phases for left turners. So again, we can have 1 phase for left turners, and if we have significant left turners in 4 directions, we can actually have now a fourth phase for, again, for the other type of movements for left turners. So those are the phases. And your goal again is to reduce, as I mentioned through the lecture recorded last week. The goal is to reduce the number of phases, because the more phases you add, the more lost time you are introducing to the system. But sometimes you're forced to have multiple phases just because you have significant amount of left turners, you have significant amount of um, again, people going through specific direction, and you have to have a phase for that specific movement. We also talked about what type of signal operations we have. We have the pre-timed operation, and we have the semi-actuated and versus the fully actuated operation. Pre-timed operation, again, this is if you get stuck in a traffic signal in the middle of the night and you are the only one at the intersection, and you wonder why you are staying there and the red light is still lasting like forever. This is because it's pre-timed. That means it doesn't have, this intersection doesn't have any load cells underneath the pavement, or it doesn't have any cameras that trigger the change in red versus the green time. And therefore those types of intersections, which actually most of the intersections, the small one, again, pre-timed intersection, those are the small intersection where two local streets are intersecting with each other. And if that's the case, again, we don't invest that much on those small intersections, and it's pre-time. If you are driving in the middle of the day versus the middle of the night, Sunday versus Tuesday, it's the same. It doesn't change regardless. While the second type of operation, this is a semi-actuated operation where actually a local street is intercepting with a major street. So I have a local street versus here a major street. And now what we do here for semi-actuated operation, actually we put the actuator, or we put a load cell, or we put a camera on the local street. And this is basically, we're trying here to give the light, again, the light is green most of the time for the major street, except when there is a call or actuation is noted on the minor approach. So basically here we're saying that the majority of the time green time will be, or green signal will be granted to the major street until there is two or three or maybe one vehicle occupying the local street, and now they want to join the major street stream traffic stream, and if there is no traffic signal there, it's going to be hard to let them join. And therefore, again, we have those actuators that sense that there is multiple vehicles at this local street, and then it gives them specific amounts, minimum amount of green time that to let them go. But then again, it triggers back to having the most of the green time to the major street. While the fully actuated operation, this is now if two major streets are intercepting each other. Let's say here in the city of Charlotte, we have the Loop 323 and Broadway. These are two major streets. We can't really predict which one is really more major or which one has more traffic, and therefore we have actually actuators on both directions. And that's why for those types of intersections, sometimes you feel you have a lot of green time, and sometimes the green time just disappear very quickly. Why is that? Because again, the two sensors on the two streets are measuring the demand on both directions and giving more green time to the one that has more traffic. As simple as that. So those are the three different types of signal operations in a nutshell. We also talked about the left turns. Again, if if there's no left turn and traffic engineering, again, the life of a transportation engineer would be way easier, but that's not the case. We do have left turns and we treat them in multiple ways, or we try to control them in multiple ways. The first type of operation when it comes to left turns is permitted left turns, and those are basically, I'm saying here that the driver is permitted to cross through the opposing flow, but they have to select an appropriate gap in the opposing traffic in order for them to go through that intersection safely. So when does this happen? Again, if it's a flashing green time, uh, that's basically the time where we're permitting the drivers to take the left turn, but under their own responsibility once they see an appropriate gap in the opposing traffic direction. While the second type of left turn operation control is the protected left turn. Protected left turn is actually made without an opposing vehicular flow. This is here the traffic signal plan protects the left turning vehicles by stopping the opposing through movement. This is now where there is a steady green lens or a steady green arrow. In this case, you as a driver, you are not taking any chances. You are actually waiting for your own for that specific time where you can cross safely, and you know that there is no opposing traffic to look for. While a newer approach to be trying to be more efficient here is to have a compound left turn. Compound traffic turn is actually it's more complicated signal timing because it can be designed in which again the traffic turns are protected as portion of the signal cycle, and they actually um, act as permitted in another portion of the cycle. So it happens sometimes again you drive through an intersection and you have a steady green for some amount of seconds, and if it's a steady green arrow or a steady green lens, that means it's a protected left turn for that instance, and you don't need to worry about the opposing traffic because you know that there's no opposing traffic during that time. And at other time of the cycle you're noticing it's again flashing green or sometimes flashing lens or flashing even yellow. That's again that mainly flashing green, and that's actually now it's acting as a permitted left turn, giving you the chance to cross if you see that there is enough gap in the opposing traffic movements. Then we start now some of the major part here of this chapter is lots of calculations, talking about the concept of discharge headway, saturation flow, lost time, and so on and so forth. One of the equations that we started with was the saturation flow rate. If how to get the saturation flow rate. Actually, if I know what's the saturation headway, if I know how much each vehicle would need to clear the intersection, if I divide 3600 seconds, which is this is how many seconds in an hour, over how much is the headway per vehicle, I'll be able to know how many vehicles are gonna clear that intersection. What's the saturation flow rate? And then we start talking about within each phase, we have some lost time. It's not only um, it's not really practical and reliable to assume that there is no lost time going between different traffic lights. There is startup lost time, for example, L1, and this is actually basically the difference between the headway of the first vehicle to the second to the fourth vehicle. And this is actually explained here. The very first vehicle, the way they respond to a green light is going to take them a little bit longer to to respond to the green light versus the second car versus the third car. But if you are on as a fifth or a sixth car, you know, you see that, you know, again that you're about to move. You see the vehicles in front of you, they are moving already, so your headway is going to be much less compared to the first, second, or even third vehicle. So that is what we call the startup time, the startup loss time. Once the green time comes in, there will be some time lost just for the first couple vehicles to start to accelerate to the highest speed. And that, again, that is what we call the startup loss time. And it's per phase. Every phase has its own lost startup loss time. And basically how we calculate it, this is actually incremental headway. And this is how we get the startup loss time. So really the startup loss time in this equation here, this is Tn, which is the green time required to move a queue of number of n number of vehicles through a signalized intersection. Is basically now what we're saying is, in reality, it's not just if I know the number of vehicles gonna cross this intersection, and if I multiply by the headway, then how many seconds needed by every vehicle to clear the intersection. Theoretically, this is all what you need. This is the only green time that you need, which is number of vehicles times the headway. But that's not the case, because now you need to add the startup plus time as well, which is actually, this is number of seconds per phase. And that's why we came up with a new definition, Tn. This is the green time required to move a queue of n vehicles. We also mentioned that there is, besides the startup loss time, there is also a clearance loss time. So that's the loss time associated with stopping the queue at the end of the green signal. So instead of startup loss time when the green light just come in, and now people are starting slow, but they pick up with time. Now actually when the green time is about to be over, people now are gonna start to they're gonna start to slow down. They are having the expectation that the green time now is about to be done, getting into the yellow time, and that is also considered what we call a clearance loss time. So in reality, the total lost time for per phase is actually a summation between L1 and L2. L1, this is again the startup lost time, plus L2, the clearance lost time. We also discussed the concept of the effective green time. Effective green time is actually, this is how much, how much time does every vehicle can use to clear the intersection. It's not just the actual green time for any movement, which is capital G. It's actually GI, which is the actual green movement, plus capital YI, which is the summation of the all red time and the yellow time, minus TLI, which is, this is the total lost time per movement. What does that mean? That means, now looking here, we're saying that effectively the green time per movement is actually whatever the green the total green time per movement, which is the green lens when it turns on, plus the all red time and the yellow time, because really those are in your favor. Having couple seconds as yellow interval and having 2 to 4 seconds as an all red interval, it's technically and effectively, this is an effective green time. You can move and clear the intersection during this time as well. Again, is it legal? Maybe not. Especially again, if it's all the time, you are not supposed to use this time. But if you had to, you had to for safety sake. But this is again, that's why we say it's the green time plus all red plus the yellow time minus TLI, which is minus the clearance time. I mean the lost time, which is L1 plus L2. If we do that calculation, we're gonna come up with what we call effective green time. This is effectively how much time these vehicle drivers have to clear that intersection. And that actually get us to this concept of the capacity of lane or any lane group, which is CI is equal to SI, which is the saturation flow rate that we've mentioned previously, which is the 3600 seconds over the saturation headway times. So really, last time, this equation right here, this is very theoretical, where we say, you know what, the saturation flow rate is simply 3600 seconds over headway. That's not the case, because really there is lots of lost time going on, and that's why we multiply the saturation flow rate by this factor or by this ratio. This ratio is actually the effective green time over the signal cycle length. The signal cycle length. And we had an example here. Let's say I have a cycle length of 60 seconds. The green time, capital G, is 27 seconds. The yellow plus all red time, which is capital Y, that's 4 seconds. The saturation headway is 2.4 seconds per vehicle to clear the intersection. The startup loss time is 2 seconds. The clearance loss time is 2 seconds. So how, how did we do that? Again, there are two ways, as I showed you in this example. One of the ways is simply to use the equation. C is equal to SI times um, GI over C. SI, this is the as I mentioned, it's saturation flow rate. So that is 3600 seconds over 2.4 times GI over C. The C, the capital C is 60 seconds. That is known. But now I need to get the effective green time. The effective green time, as we know, again, from this equation right here, the effective green time is the G plus YI minus TLI. So really, the GI here is 27, which is right here, 27 seconds, true green time, the lens time, plus 4 seconds. This is the yellow time plus the all red, minus 4 seconds. 4 seconds is actually is the summation of the 2 plus 2, which is L1, the startup loss time, and L2, the clearance loss time. So once you do this, effectively, you have 27 seconds in this cycle. So 27 over 60 times 1500, that's what's gonna get us to 675 vehicles per hour per lane. Or you can do what I did here, which is another way of doing it. If you don't want to follow the equation, you can say the following. The time in an hour is 3600 seconds. This is actually, again, the concept of you having a full pi. The pi here is 3600 seconds. How this pi is going to be divided between red time and green time and all red and yellow is actually going to help us, because the red time, we're saying here, the red time in an hour is basically 60 minus 27 minus 4. Where did we get times 60? Where did we get this from? Times 60 is basically we're having 60 cycles per hour. Per 1 hour, we're having 60 cycles. Why? Because the cycle is mentioned is 1 minute, 60 seconds. So in one full hour, I know that the we're gonna have 60 cycles. Within each cycle, the red time is actually 60, the total cycle length, minus 727, which is the green time, minus all red and yellow time. So if I have 60 seconds as a cycle length, I know that 27 of them is capital G, and I know four of them is actually the Y plus the all red. So times 60, this is here is going to give us the total red time. If the total red time is 1740, and the lost time in an hour is actually 2 seconds L1 plus 2 seconds L2 times 60 cycles in an hour. So every minute we're losing 4 seconds because of L1 and L2. So therefore 4 plus 60 cycles in that hour, we're going to lose 240 seconds. So what we're saying here is the remaining time in an hour is basically 3600 seconds minus the red time minus the lost time. This is going to give us the effective green time, which is 1620. And once you have 1620, now we can simply say this is now the pure green time, 1620 over the headway, 2.4 seconds. I'm going to have 675 vehicles per hour per lane. Or again, if you want to follow the equation, you can, which is this equation right here. CI is equal to SI times GI over C. Same thing. We're gonna come to the same answer. The the theoretical saturation flow rate, which is 3600 seconds over 24, and then you need to multiply this by the effective G over 60. Then we talked about the concept of critical lane and time budget concept. We've gone through the calculations, and then here, this is the derivation of the equation, all the way until we reach to one of the most famous equations in this chapter. The following relationship will emerge, which is VC. This is the maximum sum of critical lane volume. The maximum sum of critical lane volume is actually 1 over H, which is the saturation headway, times 3600 seconds minus N times TL over 3600 over C. 3600 seconds over C, this is the cycle length. N, I defined it for you previously, which is the number of phases in the cycle, and then the TL, this is the total lost time. And we had an example here. If the signal at this location has 2 phases, so N is 2. A cycle length, capital C, is 60 seconds. The total lost time, TL, is 4 seconds per phase. And the saturation headway, H, is 2.5 seconds. How can we get the maximum sum of critical lane flow? The equation is simple. Let's read this here and take a look at the equation. So 1 over 2.5, this is the headway, over times 3600 minus 2 times 4. 2, this is the 2 phases per cycle, times 4, this is the last time, times 3600 over 60 seconds, which is the cycle length. This is going to give us a total maximum sum of critical lane volume or flow, 1248 vehicles per hour. But also we looked into now what are the factors that actually affect the sum of critical lane volume, because that's important to us, and our goal as traffic engineers, we want to increase that VC as much as we can. So really here again, we've gone through this, but the longer the cycle length, the fewer cycles there are in an hour. So sometimes increasing the cycle length, that's a good thing. So here the cycle length, again, if we have a cycle length of certain amount here versus here, so as you could see, regardless of how many how many phases, we're gonna end up with high sum of critical lane volume compared to if I have a small cycle length right here. But also what's important is how many phases. That's also important. If we have number of phases 2, only 2 phases in that cycle, we're gonna end up with a high sum of critical lane volume. This is the minimum, this is the maximum if I have 2 phases only. But if I have 4 phases, I'm gonna end up now with much lower sum of critical lane volume. Why? Because each phase is going to have its own associated lost time, which is the startup lost time and the clearance lost time. So we have to keep that in mind. So you have the cycle length as a factor, and you have the number of phases as another factor. But again, at certain point, and that's why I'm having this disclaimer here, if you will. Again, capacity can rarely be increased significantly, as you could see, by increasing the cycle length. At certain point, this line actually again is plateauing. So you see here, so it's not really increasing like that. It's actually it's we're gonna reach a certain value that we're not gonna increase the sum of critical lane that much by reducing the number of phases or by increasing the cycle length. The better option once you reach to that plateauing value is actually now you need to think of increasing the number of lanes. Adding lanes are often necessary and in such conditions. And speaking of number of lanes, this is actually now where we start talking about finding an appropriate cycle length. What would be the appropriate cycle length? Here, again, we know that small cycle length, that's not gonna be enough, but also a very high cycle length, we're gonna reach a certain plateau, and that's not gonna be efficient. So what is the minimum cycle length? So we started with this very theoretical equation for what's the minimum cycle length, but actually we did a correction, and this is actually the equation that we use, which is the design cycle length, not the minimum cycle length. The desirable cycle length actually is n, which is number of phases, times TL, the last time, over 1 minus V over C over 3600 over H times PHF times V over C. So here what we did, compared to the previous equation, we included these two new factors, the peak hour factor as well as the V over C. And again, that's the difference. So previously, again, with the C minimum equation, it again, we modified it by adding those two factors to have more of a realistic evaluation, because we need to include the peak hour factor, because the peak hour factor, this is what's going to give us the worst hour, the worst 15 minutes in the peak hour. And also, I don't want to use up all, I don't want to use up all the capacity that I have. That's why I have the V over C factor here. A question here is asked, can we pick. Oh, that's not related. I thought, okay. So the question here is, can we pick our first exams? Um, the solution for the exam is not posted, and I will not post it because we reuse those. Sometimes we reuse those equations. You can pick up your exam. You can come here, see it. You have all the time, but then you're gonna give it to me back. All right. Let's keep going here. So we had an example here for the desirable cycle length, and then here also we have the V over C. Again, V over C having, if I have V over C of 80% versus 100%, your goal is to have a V over C as low as possible. V over C, this is the volume versus the capacity ratio. You don't want to have your network at 100% all the time. That's you're going to end up having lots of issues, lots of considerable amount of delays, and even increased chances of having more um, traffic incidents, and mainly again traffic accidents. So this is just to give you an idea of the sum of critical lane volume versus the desirable cycle length relationship, where if I want to have again V over C equal to 100 or 100% or 1, again the sum of critical volume versus the desirable cycle length, the cycle length now is going to end up being very small, and a small desirable cycle length, that means more phases, and that means more lost time versus the 80%. And then here we have this great example, um, where now we need to consider the case of three-phase signal, um, with the TL of certain amount and saturation headway of 2.2 seconds per vehicle. I gave you the peak hour factor, and now actually we are going through. This is really a design problem where we're varying one option, which is the target ratio V over C from 1 to zero point 0.8, and see what would the that impact, how much would that impact the desirable cycle length. Desirable cycle length, if I'm using the full V over C of which is 100% or 1, I need a desirable cycle length of 65 seconds. But again, that's really you're pushing it. It's 100%. So we went now from 1 to 95%, which is 0.95, and now the desirable cycle length is 85 seconds. That's fine. You are increasing your desirable cycle length in order to let more people go, but at the same time you're reducing the lost time, and also now you're using 95% of your capacity instead of 100%, which is not really recommended. How about if someone want to be more conservative and say, you know what, instead of 95%, why not 90%? 90%, you're gonna end up now with a cycle length of 130 seconds. You may say, okay, so what? That's fine. How about 85% V over C? 85%. Now we're gonna end up with 290 seconds desirable cycle length. This is now you're gonna be have lots of disappointed people. The cycle length now is significantly longer, 290 seconds, just to keep the V over C over 85%, or at 85% or lower. And if you really now want to go to the extreme goodness, which is 80%, what do you want to, what are you going to end up with having now? We're going to have a negative desirable cycle length. The negative here doesn't mean anything, but it means that there's not enough time here within this hour to accommodate the demand with the required green time plus the 12 seconds less time per cycle. That's basically what it is. So really here you are somewhere stuck between V over C of 100% at 65 seconds, or all the way down to 85% at 290 seconds. Again, I will pick somewhere between these two values to tell you the truth, which is again either somewhere between 90 to 95%. So basically somewhere between 85 to 130 seconds. Typically, maybe here again, 120 seconds would be my recommendation. We had another example here. This is an important example where we needed to know now, based on what's the maximum critical lane, the maximum sum of critical lanes V over C was 1357 vehicles per hour. And if I know these numbers here, which is the cycle length is 60 seconds, the the last time is 4 seconds per phase. I have two phases. The peak hour factor is 0.95. The target, your target V over C ratio is 90%. So this is given to you now. You're not designing that, and the headway is 2.3 seconds per vehicle. But this problem is asking you is how many lanes per directions you need to have to satisfy the maximum sum of critical lane. So really here again, we've gone through this calculation. It's mentioned in details in the recorded lecture, but basically we're saying that if we have, um, again, this is the V over C is 1357, we should not exceed that. And again, um, the critical southbound volume is 1200 vehicles per hour. So that 1200 and in the opposite direction, which is the eastbound is 1800. So really here, if I have one lane per bound to handle this amount, that means V over VC, the capacity is 1200 plus 1800, and that's 3000 vehicles per hour for this critical lane. While we know that the maximum sum of critical lanes have to be 1357. And that's why we start saying, you know what? How about now we go to the worst bound, which is the 1800, the east westbound, and now you say, you know what? I'm gonna have two lanes. So that means that 1800 critical volume is gonna be split 900 each. And now the V over C is actually we're gonna pick the worst from each. This is the critical lane concept anyway, which is we pick the 1200 plus 900, and that is 2100 vehicles per hour. Still not good. Why? Because it's higher than the maximum sum of critical lane giving this information. So we go to to this bound, the north-south bound, and we split the 1200 to 600 each. And now the sum of critical lane volume is actually 900 plus 600, and that is 1500 vehicles per hour, and that's also not good. Why? 1500 still higher than 1357. So we keep going, and now we go to the worst bound, which is in this case now the east-west bound, the 900. And instead of that, we say, you know what? For the original 1800, we're gonna split it into 3 lanes instead of 2 lanes, and that's why here we have 600 3 times, while this north southbound is just 2 lanes. So now the V over C, the critical volume, the critical lane volume is actually 600 from one of these 2 lanes plus 600 from one of these 3 lanes. And now it's 1200, which is okay. Why? Because now it's less than the maximum sum of critical lanes, which is 1357. And therefore, your conclusion here, or your design rather, you have to have 3 lanes per direction in the east westbound. You have to have 2 lanes per direction in the north-south bound. And the last thing here we wanted to do is what's the desirable cycle length for this for the previous problem, knowing that now the VC is only 1200, is not 1300. So this is here where you start the cycle length was 60 seconds, but that 60 seconds is based on having the maximum sum of critical lanes is 1357 vehicles per hour. But once you go through the calculation, and now you're designing an infrastructure that can handle or that the maximum is actually 1200 vehicles, so you need to revise the equation. So that's why the desirable cycle length is 2 times 4. Everything is the same, but this here, instead of having 1357, now we're having the real number, we're reducing it, which is good, is 1200. And therefore now the desirable cycle length is 77.7 seconds. Please do not program this number again, it's weird. So we pump it up to 80 seconds. So instead of the original cycle length was 60 seconds, but now after now the design problem, and we know now that there are 3 lanes in the east westbound, and we have 2 lanes in the north southbound. This triggers now that the maximum critical lane is volume of flow is 1200, not 1357, and therefore we have to repeat the calculation. And now the new desirable cycle length is 80 seconds, not 60 seconds. Here again, another, this is a scenario here, imaginary scenario that I covered. If the space limited, how about now? Your design is 3 lanes in the eastbound, in the east-west bound, and 2 lanes in the north-south. You present this to your boss, and they said, well, there's no way to do 3 lanes. We're gonna be limited. If the space, the right of way, back to chapter 1 or 2, right of way, we do not have the right of way to have 3 lanes in both in each direction. Rather, we are limited by 2 lanes. Can we live with that? Having 2 lanes, this will result now in a VC of 1500. Where did we get the 1500? Right here. This is the 1500. If we have a VC of 1500, so we're stuck with 1500 vehicles per hour. What would be now the desirable cycle length to handle a VC of 1500 rather than 1200? So we use the same equation. C desirable is 2 times 4. It's not actually, it's not 1200 anymore. It's 1500. What happens? You have negative 66.1 seconds. What does that mean again? Once you see a negative and from the desirable cycle length equation, that means you can't have 2 lanes. And actually, again, the negative result indicate that there's no cycle length that can accommodate a VC of 1500 vehicles per hour for this location, and therefore you have to stick to your guns. Basically, again, show the equation, and you just can't have 2 lanes in this location if you're gonna um, if you're gonna have again a make sense desirable cycle length. So that's actually again in a nutshell what we covered in this chapter here. It's a very important chapter, and it's a good introduction for what's gonna be expanded on next
next myth.